The world is experiencing record-breaking temperatures. July 2023 was recorded as the hottest month globally. March 2023, India received its first heat wave of the year. And World Meteorological Organization predicts there will be even hotter times in the next 5 years. This means more and more air conditioning to cope with the heat. This not only poses a public health threat, but also upsets the energy budget of the country. According to Niti Aayog, India Energy Security Scenario 2017, 65% of the energy demand in the building comes from space, cooling and heating. This is only going to surge with increasing extreme weather events. My name is Rajneesh Sareen. I lead the program on green buildings and sustainable habitat at Center for Science and Environment. In 2019, India became amongst the first countries to launch a cooling action plan. Its targets include reduction in cooling demand across sectors by around 25% and reduction in cooling energy requirements by around 35% by 2038. The plan also points out need for non-refrigerant based and not-in-kind technologies. Not only its focus on sustainable cooling, it mooted the idea of thermal comfort for all. This could be achieved by passive strategies like shading, ventilation, insulation, amongst other, before adopting any active or mechanical cooling measures. Indian traditional architecture recognizes that building needs to respond to the native climate and geography. It has followed a bioclimatic approach to design and choice of materials. Site planning, building forms, envelope, materials, opening sizes, even vegetations are all tweaked in response to the local context to achieve this bioclimatic design. This makes the occupant thermally comfortable with little or no dependency on active cooling measures. This knowledge has been refined over the generations to ensure comfort of occupants in diverse thermal conditions and has come to us in the heritage. The accumulated wisdom and adaptability has safeguarded India's built environment from excessive reliance on mechanical cooling systems. As a result, India maintains a remarkably low per capita space cooling energy consumptions of 69 kilowatt-hour per person, which is nearly 4 times less than the global average. Environment, aspirations and expectations all have changed. Cities have become denser. Vegetation and water bodies have decreased and we are producing more heat within our cities. This has affected the ambient temperature itself. CSE is working on this issue where we look at the cooling on the city scale. The other factor is that people's idea of thermal comfort has changed. As quicker solutions to cooling have dominated the market, especially the continuous use of compressor-based air conditioning. The repercussions are already showing in the form of huge energy cost and human health impacts. The combination of these factors is expected to create a surge in cooling demand, not just in India but globally. Ministry of Environment, Forest and Climate Change recognizes this and estimates the cooling demand in the building to grow 11-fold by 2037-38 when compared to 2017-18 baseline. The answer lies in fully utilizing the knowledge of the cooling web. This web is looking at both passive and active solutions that achieve cooling. More importantly, it also deciphers the chronology of the application in the built environment. The passive measures represent the strategies that enhance microclimate. This includes vegetation, water features, permeabilities, etc. and their relative placements in the context with the built spaces, built forms, envelope and materials. Interplay of these elements effectively brings up a desired thermal response, shading, ventilation and daylighting strategy for a built project. The next step is a little more trickier as we are going to work with the changing weather around us, which is more influenced by the climate change. To get a desired level of thermal comfort inside the structure throughout the year, we may require a help from a psychometric chart. This includes physical and thermodynamic properties such as dry bulb temperature, wet bulb temperature, humidity, air density, etc. This drives the choices of low-impact cooling solution. Example, adiabatic cooling, wherein technologies like evaporative cooling are looked upon. Weighing the energy consequences of the desired cooling strategy, we can arrange cooling solutions stage-wise and season-wise. This could be supplemented with the abundant and natural renewable reserves like geothermal, solar energy, wind potentials, etc. Rest of the cooling demand could be augmented by the mechanical cooling. This chronology has the power to bend the curve of energy use in cooling. This is the domain of cooling web. This blend of context-appropriate design and technology has been documented by CSE in the form of multiple case studies. They represent a range of cooling solutions that are diverse and comprehensive and do not rely on conventional energy guzzling practices. Anil Agarwal Environmental Training Institute in Nimli, Rajasthan, the campus has used a 3-stage cooling system, which includes indirect and direct evaporative cooling. NIIT University Neemrana and Sabakhand building inside the Gujarat Vidyapeeth in Ahmedabad, which uses the potential of earth to absorb heat by employing an earth-air tunnel system. IIT Gandhinagar in Gujarat and Indraprastha Institute of Information Technology in Delhi that use district cooling systems and a passive downdraft cooling system. We need to reduce emissions. We need to learn to adapt to this changing climate. CSC will continue to research on what needs to be done and to advocate for the policy and practice changes so that we can build wisely.
A new episode of Call for Action on the most pressing issues will be out every Friday. Press the bell icon for regular notifications. For further information on sustainable habitat, please visit us at www.cseindia.org. And for more engaging content on science and the environment, subscribe to the Down to Earth YouTube channel.